One fleet sits at 15% CPU all day, burning money on capacity nobody uses. Another slams the system every weekday at 6 in the morning. They look like opposite problems, and a single Amazon Web Services service fixes both. Stack Lessons, Episode 17, Answer Incoming. By the end of this video, you'll be able to look at any described load pattern and name the exact scaling policy that fits it. We'll cover auto-scaling groups and the 4 policy types, and how choosing between them is both a resilience decision and a cost decision. In the last episode on load balancing, we saw how an application load balancer spreads traffic across healthy targets in multiple availability zones, and how health checks decide which targets actually receive requests. But a load balancer only distributes traffic. It never creates or destroys the servers behind it. Something has to add instances when load rises and remove them when it falls. That something is auto-scaling. Before we get into the mechanics, 5 terms worth having sharp in your mind. First, the auto-scaling group itself, a managed fleet of EC2 instances that spans multiple availability zones within a single region, launching and retiring instances on your behalf. Inside that group, 3 numbers govern the fleet size: a minimum that sets the floor, a maximum that sets the ceiling, and a desired capacity that tells the group where to aim right now. Each new instance the group launches follows a launch template, a versioned blueprint that captures the AMI, instance type, security groups, and startup script. A scaling policy is the rule that moves that desired number up or down. And there are 4 distinct policy types we'll cover one by one. Finally, a warm pool is a reserve of pre-initialized instances sitting ready so that when scale-out fires, the group can draw from warm capacity rather than booting from scratch. Look at MegaCorp's 2 problems side by side. On the left, a cost problem. The fleet was sized for peak load and then never scaled back down, so it sits at 15% CPU day and night, paying for capacity that just sits there. That fleet needs to shrink when load drops. On the right, a resilience problem. The batch report jobs fire every weekday at 6 in the morning, and the baseline fleet can't absorb that surge. That workload needs the fleet to grow, and to grow before the jobs even start. One needs to get smaller. The other needs to get bigger ahead of time. Same service, 2 different levers. So what actually is an auto-scaling group? At its core, it's a manager that keeps the right number of EC2 instances running. It launches instances when it needs more, terminates them when it needs fewer, and replaces any instance that goes unhealthy. That's the foundation everything else in this video sits on. Before we talk about clever scaling policies, understand that even a group that never changes size is doing valuable work, because it's constantly keeping the fleet healthy. The Amazon Web Services documentation describes the self-healing behavior directly. If an instance becomes unhealthy, the group terminates it and launches a replacement. That's the part people overlook. Autoscaling isn't only about elastic growth and shrinkage. It's also a fleet health manager that quietly repairs failures for you. A static fleet without an ASG needs a human to notice a dead instance and rebuild it. With an ASG, that recovery happens automatically, every time, without anyone paging the on-call engineer. Every ASG is bounded by 3 numbers. Minimum is the floor. The group always keeps at least this many instances running. Maximum is the ceiling. It never launches more than this, which is your cost cap. And desired is the target it's trying to reach right now. Scaling policies work by moving that desired number up and down, always staying between the floor and the ceiling. Here's a useful edge case. If you set minimum, desired, and maximum all to the same value, the group never scales elastically at all. It just keeps exactly that many instances alive, replacing any that fail. That's pure self-healing, and it's the right answer when a scenario asks, how to maintain a fixed number of instances with automatic failure replacement. Think of it like a contract with a staffing agency. The minimum is your guaranteed headcount. You've promised there will always be at least 2 people on every shift. The maximum is your budget cap. Never send more than 20 in a single day. And desired is what today's schedule actually calls for. The scaling policy is the floor manager on the phone saying, send 3 more, or telling the agency we're overstaffed, stop sending. 3 numbers, 3 clear roles. Now, self-healing is only as good as the health check behind it, and there's a real distinction here. EC2 status checks confirm that the virtual machine is running, but a machine can be running perfectly while the application process on it has crashed. The instance looks healthy, so traffic keeps flowing to it, and users keep getting errors. That's the silent failure. ELB health checks fix this by probing an actual application endpoint, something like /health. If the app doesn't answer correctly, the instance gets marked unhealthy and replaced. So the rule is simple. When a load balancer fronts your group, use ELB health checks, not EC2 checks alone. Otherwise, you'll happily route traffic to a broken app. Here's a subtle one that has caused real outages. The health check grace period is a window that protects a newly launched instance from being terminated before its application finishes starting up. In the console, that grace period defaults to 300 seconds. But when you create a group through the CLI or an SDK, it defaults to 0. 0 disables the protection entirely. So the app is still booting, the health check fails, and the group kills the instance and tries again, over and over. If you ever see instances being terminated moments after launch, suspect a missing grace period. Always set it to at least your application's real startup time. When your group spans multiple availability zones, auto-scaling tries to keep an even number of instances in each zone. Picture 3 zones. If the middle zone becomes impaired, the group redistributes that lost capacity to the 2 healthy zones automatically. Then, when the failed zone recovers, the group rebalances back, spreading instances evenly again. The key detail is how it rebalances. It launches new instances before terminating old ones, launch before terminate, so availability never dips during the shuffle. And because of that, the group is allowed to briefly exceed your maximum capacity by 10% or 1 instance, whichever is greater. That matters because if you set your max with 0 headroom, rebalancing can stall. Think of a restaurant chain with 3 locations. One has a kitchen fire, customers reroute to the other 2, and when it reopens, everyone spreads back out. The chain never fully closes. So how does the group know what an instance should look like? That comes from a blueprint. The old blueprint was called a launch configuration, and it's a dead end. It can't be versioned or edited, it locks you to a single instance type, and it can't mix spot and on-demand instances. Account created since October 2024 can't even make new ones. The modern replacement is the launch template. It's versioned and editable. It supports multiple instance types in one group. It lets you blend spot and on-demand for cost savings, and it unlocks the newest EC2 features. Amazon Web Services is clear on this. Always use launch templates. If you see a launch configuration in an answer choice, the modern template is almost certainly the better call. There are 4 scaling policies, and each one matches a different shape of demand. Target tracking is for unpredictable or gradually varying load. You set a goal and it follows. Step scaling is for bursts where the size of the breach should change the size of your response. Scheduled scaling is for a known time-based spike where you already know the clock. And predictive scaling is for recurring, cyclical demand that repeats daily or weekly. Here's the mental model to carry through the rest of this video. The keyword in this scenario tells you which policy fits. Unpredictable means target tracking. A specific time means scheduled. A repeating cycle means predictive. Tiered bursts means step. Amazon Web Services describes target tracking with a thermostat analogy, and it's genuinely the clearest way to picture it. You pick a metric and a target value, and auto scaling creates and manages the CloudWatch alarms that trigger scaling for you. It's exactly like setting a thermostat. You choose your target temperature, walk away, and the system turns the heat up or the cooling on to hold it there. You never touch the controls again. That set it and forget it quality is why Amazon Web Services recommends target tracking as the default for load you can't predict. Let's get concrete about how target tracking behaves. You pick a metric and a target value, and Amazon Web Services builds and manages the underlying alarms. You don't touch them. The predefined metrics you'll reach for most are average CPU utilization, network in or out, and ALB request count per target. One important rule: never manually edit or delete the alarms it creates, because that breaks the policy's behavior. And as of late 2024, target tracking got sharper. It can now react to sub-minute metrics down to 10-second resolution, and it self-tunes its responsiveness to your workload's own history. That makes it an even stronger default for load that varies unpredictably. When you run more than one target tracking policy at once, there's an asymmetry worth remembering, and it always favors availability. The group scales out if any single policy says scale out, but it only scales in when every policy agrees it's safe to scale in. So if you're tracking both CPU and request count together, the group is aggressive about adding capacity and cautious about removing it. Amazon Web Services designed it this way on purpose. When in doubt, keep servers running. Now let's solve MegaCorp's first problem: that fleet idling at 15% CPU around the clock. Apply a target tracking policy with a goal of 50% CPU utilization. During off hours, when actual load is low, the policy is the fleet running well under target and scales it in, removing instances the group doesn't need. The reduction during quiet periods can reach 60 to 70% of the instance count, and the bill drops right along with it. Nothing about the workload changed. The fleet simply stopped paying for capacity it wasn't using. So why would you ever choose step scaling over that tidy thermostat? Because sometimes the size of the problem should change the size of your response. With step scaling, you create the alarm yourself and define step adjustments tied to how badly the metric is breached. For example, add 10% capacity when CPU hits 60, add 30% when it hits 75, and add 40% when it reaches 85. Think of it like hospital triage. A minor case gets a nurse, a critical case gets a full surgical team. There's one more property that matters. Step scaling keeps evaluating new alarms even while a scaling activity is already in progress. So reach for it when a single steady-state target just isn't fine-grained enough. There's an older policy type called simple scaling, and you should know why it's been left behind. Simple scaling fires one adjustment, then pauses for a cooldown period before it will respond to anything else. During a fast-moving spike, that pause is exactly when you need the group to keep reacting. Step scaling doesn't pause. It continues evaluating alarms mid-activity. That's the primary functional gap between them, and Amazon Web Services now explicitly recommends against simple scaling. If both appear as options, step wins. Let's take a quick breath and consolidate. An auto-scaling group is a self-healing fleet manager that spreads instances across multiple availability zones. Launch templates are the modern blueprint, and launch configurations are a dead end. And the two dynamic policies we've covered both react to real-time metrics: target tracking for holding a steady goal, step scaling for tiered bursts. Both of those are reactive. They wait for load to show up, then respond. Next, we look at the two proactive policies for demand you can actually see coming. Now for MegaCorp's second problem, the 6 a.m. batch spike. Since we know exactly when it hits, we don't need to react at all. We schedule ahead. This is scheduled scaling. The first action uses a cron expression that reads 06 Monday through Friday, meaning 6 in the morning UTC on weekdays. It sets desired capacity to 10, pre-positioning the fleet before the report jobs even start. The second action fires at 8 a.m. once the jobs finish and returns desired capacity back to 2. No cold start lag, no waiting for CPU to climb. The capacity is simply there when the work arrives. Picture a stadium on game night. Management doesn't wait until cars start piling up at the gates to call in extra parking attendants. They know the game starts at 7, so they schedule the crew to arrive at 5:30 before the rush. That's the whole idea behind scheduled scaling. The signal isn't the size of the crowd, it's the clock. When you already know the time demand will hit, reacting to metrics is slower and riskier than simply being ready. A few mechanics make scheduled scaling reliable. It uses standard 5-field Unix cron, minute, hour, day of month, and day of week. Times default to UTC, but you can specify a name time zone, like America/New York, and it'll adjust for daylight saving automatically. A scheduled action sets desired, minimum, or maximum capacity directly at the chosen time, not through a metric. And 2 practical limits. You can define up to 125 actions per group, and an action may run up to 2 minutes late, so build a little buffer into your timing. This is the mistake that shows up constantly, so let's name it directly. The tempting fix for a daily 2-hour spike is to just leave 10 instances running all the time. It works, but the fleet sits idle 22 of those hours. That's the exact anti-pattern a FinOps audit flags. And the root cause is simple. You're running 10 instances 24 hours a day for a 2-hour window, paying for peak capacity all day, every day. Scheduled scaling gives you the same peak coverage, 10 instances during the batch window, and then drops back to 2 the rest of the day. Same resilience during the spike, up to 80% cheaper for that fleet. When a known pattern exists, static overprovisioning is almost never the right answer. But what if your demand repeats on a cycle, yet you can't write a single clean cron line for it? That's where predictive scaling comes in. As Amazon Web Services puts it, predictive scaling analyzes historical load data to detect daily or weekly patterns, then forecasts future capacity so auto-scaling can proactively grow the group ahead of the anticipated load. Instead of you specifying the times, a machine learning model learns them from your traffic history. Think of a surfer reading the tide charts and positioning for the wave before it breaks, rather than paddling frantically after it's already crested. Dynamic scaling is the frantic paddler. Predictive scaling is the surfer who planned ahead. Here are the numbers that define how the forecast model works, and they come up often. First, it needs at least 24 hours of data before it can forecast anything at all. From there, it analyzes up to 14 days of history to detect daily and weekly patterns. It then produces an hourly forecast for the next 48 hours. That forecast refreshes every 6 hours as new CloudWatch data arrives, so it keeps getting sharper. And finally, using a scheduling buffer time, it pre-launches instances a little ahead of the forecasted peak, so capacity is warm before demand actually lands. One critical limitation to internalize. Predictive scaling only ever scales out. It pre-positions capacity for the coming peak, but it will not remove instances once the peak passes. So predictive scaling never works alone. You pair it with a dynamic policy, usually target tracking, to handle the scale-in. Predictive forecasts the wave and gets you ready. Target tracking cleans up afterward and trims capacity back down. And when both are active, the group always uses the larger of what any policy asks for, so you're never under-provisioned. This hybrid isn't theoretical. Netflix proved it at massive scale years ago. Back in 2013, they built an internal engine called Scryer that studied historical traffic patterns and provisioned EC2 capacity hours in advance. On top of that, they layered reactive auto scaling as a safety net for surges Scryer didn't see coming. Amazon Web Services started moving in this direction in November 2018, when predictive scaling appeared as part of Amazon Web Services auto scaling plans, a separate service sitting above individual groups. It wasn't until May 2021 that predictive scaling became a first-class native policy directly inside EC2 Auto Scaling groups. So the design Amazon Web Services recommends today is the one hyperscale companies had to build themselves years earlier, forecast for the wave, then react to whatever actually arrives. There's one more mechanic that ties resilience and cost together, and it solves a problem the policies don't. Some instances take a long time to boot. They write huge amounts of data to disk, or run a lengthy bootstrap before they can serve traffic. When a scale-out fires, that boot time is dead weight. As Amazon Web Services puts it, a warm pool decreases latency for applications with exceptionally long boot times, and it means you no longer have to over-provision running instances just to hide that startup lag. A warm pool keeps pre-initialized instances in one of three states, and the choice is a cost decision. Stopped is the recommended default. You pay only for the EBS volumes and any elastic IPs, so the compute cost while idle is essentially nothing. To put numbers on it, keeping 10 instances stopped in a warm pool runs around $2 a month in storage versus well over $1,000 if you kept them all running as standby. Hibernated keeps a RAM snapshot for faster resume at a bit more storage cost. Running keeps them fully stored at full price. Generally avoid that. Warm pools do require an EBS-backed root volume, and they're only worth it when boot time genuinely hurts your users. Think of a relay team warming up in the holding zone, ready to step in the instant the baton comes. And the real-world payoff is large. Palo Alto Networks, whose firewalls have a multi-minute bootstrap before they can pass traffic, cut their in-service time by up to 80% using warm pools in the stopped state. HackerRank saw their node readiness drop from roughly 5 minutes to about 70 seconds, around a 77% improvement, while eliminating outages during scale-up events. Both got faster and cheaper at the same time because stopped warm instances cost almost nothing while they wait. One caveat, though, because it's easy to get overexcited about warm pools. Amazon Web Services warns directly that creating a warm pool when it isn't required can lead to unnecessary costs. Every pre-initialized instance still adds EBS storage charges. If your instances boot quickly and there's no noticeable latency when the group scales out, you don't need a warm pool at all. It's a fix for slow boot workloads specifically, not a default you sprinkle on everything. Now let's assemble MegaCorp's complete design and watch the pieces click together. It starts with a launch template holding the AMI, instance type, and security groups. That feeds one auto-scaling group spanning 3 availability zones with a minimum of 2 for an always-on baseline and a maximum of 20 as the cost cap. On top of that group sit 3 policies that coexist safely. Scheduled action handles the 6 a.m. Batch spike, pre-positioning capacity on the clock. Target tracking at 50% CPU smooths out the ordinary day-to-day variation. And once there's enough history, predictive scaling anticipates the weekly cycle. Underneath, a stopped warm pool keeps slow boot job runners ready, and ELB health checks catch application-level failures the EC2 checks would miss. One design, and it solves both the idle cost problem and the spike problem at once. And to be clear, running these policies together isn't a hack. Amazon Web Services explicitly encourages it. The documentation states you can use scheduled scaling and scaling policies together, and that after a scheduled action runs, the dynamic policy continues making its own decisions about whether to scale further. So the scheduled action sets your base capacity for the batch window, and target tracking fine-tunes on top of it in real time. That layered approach is the reference architecture for workloads that are predictable but still variable. Before we close, 4 mistakes that consistently break auto-scaling in production. First, the health check grace period defaults to 0 in the CLI and SDK, which effectively disables it. Always set it to match your application's startup time. Second, when a load balancer fronts the group, use ELB health checks rather than EC2 checks alone, so a crashed app actually gets replaced. Third, raw SQSQ depth doesn't work as a target tracking metric because it doesn't shrink as you add instances. Use a custom messages per instance metric instead, which is exactly how MegaCorp scales its worker fleet. And fourth, auto-scaling groups are regional. They span multiple availability zones, but not multiple regions. So cross-region failover needs something like Route 53 or a global accelerator on top. So here are the decision rules to carry forward: unpredictable or gradually varying load points to target tracking. A known time-based spike, like MegaCorp 6 a.m., batch points to scheduled scaling. Recurring cyclical demand points to predictive, paired with a dynamic policy to handle the scale-in. And a multi-threshold burst that needs different responses at different severities points to step scaling. Above all, remember the two-sided payoff. Auto-scaling buys you availability through self-healing across zones, and cost savings by scaling in when the fleet is idle, not one or the other, both at once. Now let's see how well all of this stuck with a quick 5-question quiz. Question 1. A company's EC2 batch report jobs run every weekday, starting reliably at 6 in the morning UTC and finishing around 8. The baseline fleet can't absorb the surge, and a purely reactive policy adds capacity too slowly. Which scaling approach best fits this pattern? Is it A, scheduled scaling that raises desired capacity before 6 and lowers it after 8? B, target tracking on average CPU at 50%. C, step scaling with 3 CPU thresholds. Or D, predictive scaling in forecast-only mode. Run the policy to pattern rule before you answer. The right call here is A. The demand hits at a known fixed time, so scheduled scaling prepositions the fleet before 6 and drops it back after 8. Reactive policies wait for the metric to climb, which is exactly the cold start lag you want to avoid when the clock already tells you what's coming. Question 2. An engineer creates an auto-scaling group through the Amazon Web Services CLI. Newly launched instances are being terminated within seconds of starting before the application finishes booting. What is the most likely cause? A, the maximum capacity is set too low. B, the launch template is missing an AMI ID. C, the health check grace period defaulted to 0 because the group was created through the CLI. Or D, the group spans only one availability zone. Lock in your answer before I give it away. It has to be C, and here's why. The grace period defaults to 300 seconds in the console, but 0 over the CLI or an SDK. 0 disables the protection, so the group kills each instance before the app can pass its first health check. Set the grace period to your application's real startup time, and the problem disappears. Question 3. A team enables predictive scaling to get ahead of a recurring weekly traffic pattern. After the peak passes each week, the fleet stays large and never shrinks. What is missing from their configuration? A larger maximum capacity setting. B, a dynamic scaling policy to handle scale-in, since predictive scaling only scales out. C, a second predictive scaling policy for scale-in. Or D, a longer scheduling buffer time. Think about which direction predictive scaling actually moves. This one is B. Predictive scaling only ever scales out. It prepositions capacity for the forecasted peak, but never removes it. You always pair it with a dynamic policy, usually target tracking, to trend the fleet back down once demand falls off. Question 4. An application's load varies unpredictably throughout the day, with no clear time-based or cyclical pattern. The team wants a low-maintenance policy where Amazon Web Services manages the CloudWatch alarms automatically. Which policy should they choose? A. Simple scaling with a cooldown period. B. Scheduled scaling with hourly cron actions. C. Step scaling with manually defined alarms. Or D. Target tracking on a metric like average CPU utilization. Got your pick? Let's see. The answer is D. Target tracking is the recommended default for unpredictable, gradually varying load. You set a metric and a target value, and Amazon Web Services builds and manages the alarms for you, the thermostat model. Step scaling makes you manage alarms yourself, and simple scaling is deprecated. Question 5, and this one revisits an earlier episode on decoupling. A worker fleet drains an SQSQ, and a team wants auto-scaling to add consumers as the backlog grows. Which metric should drive the target tracking policy? A. The raw approximate number of visible messages, the queue depth. B. A custom backlog per instance metric, queue depth divided by instance count. C. The load balancer's total request count. Or D. Average CPU utilization of the consumer instances. Pause here if you want more time. If you said B, well done. Raw queue depth doesn't shrink as you add instances, so it can't drive target tracking correctly. The backlog per instance metric, messages divided by current instance count, scales proportionally, which is exactly why MegaCorp uses it to scale its SQS worker fleet instead of CPU. That's the end of EC2 Auto Scaling strategies. Subscribing keeps these free and pushes them to more people prepping like you. So if it helped, please do. Let me know in the comments what landed and what didn't. If you got a cert you want next, the comments are open. And if the style or the speed could be better, I want your honest take. See you in the next lesson.